Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 11 of an 11-part mini-series within that larger playlist. This mini-series deals with hierarchical designs, and the data is from statology.org. And we load the data. So we're looking at the growth of a plant, and the two factors are fertilizer and then the technician that's applying that type of fertilizer. And we load it here. And the difference is the way we load technician. And perhaps I should just show you the data. So here we have technician 1, 2, 3 within A, and then within B we have 1, 2, 3. But they're actually different technicians, even though we use the same numbers 1, 2, 3. And for the second data set, we label them 1, 2, 3, 4 through 9. Because they're different technicians. Now, usually they go with the first approach where they just relabel them 1, 2, 3, 1, 2, 3. But here, if we run the analysis using the data set DF and the data set DF2, the numbers are 100% the same. And it's because technician is nested within fertilizer is the reason that it doesn't matter. Now, let's go to part 1, model development. A, fertilizer has 3 levels. B, technician, it kind of has 3. It has 3 levels within a level of A. So that's why B is 3. We're going to put the growth in the Y variable. We're going to create 2 data matrices, one for factor A, one for factor B. We're going to populate it. 1 is the column of 1s in the first column, and so this is the design matrix. And to me, I learned so much by studying the design matrix. So of course the first column is associated with the mu parameter. The next 3 columns are associated with factor A, and then look at the next 9 columns. Right, there's 3 levels within 3 levels of B within each level of A. So there's 9, but they each get their own effect because they're different technicians, or they're nested within factor A. And then there's 4 replications each. Now we need to create the perpendicular projection matrices onto these column spaces. So we have the identity matrix J, perpendicular projection matrix on the column space of 1s, MA, MB, and M. M is a perpendicular projection matrix on the whole column space. But it turns out the column space of factor B is equal to the whole column space. So like the first column of 1s is a subset of the column space associated with factor B. The column space associated with A is a subset of the column space of B. So M and MB are equal, and we test that, and it's all true. Now, these next 3 lines are going to come back when we look at contrast. So here's a least squares estimate for the beta parameter. So the first one, the 13, deals with the mu parameter. The next 3 deal with alpha 1, alpha 2, alpha 3. And then the next 9 deal with factor B. And let's look at the means. This is the mean of factor A, B, and C. And here are the means of each of the technicians, or the levels of factor B. Right? Okay. And again, that'll come back when we look at contrast. So again, this is the design, or how you enter it into R. You say fertilizer / tech. That means technician is nested within fertilizer. And here is the Anova table. Now, technically, it's over parameterized, and there's different ways you can represent this model with the same thing. And here's one example, that if we do a two-way interaction but we remove the factor for tech, this is actually the same model. And if you compare each of these Anova tables, they're 100% the same. So it depends upon how you think about this model. But usually you use the first representation. Now, if we look at the sums of squares associated with each of these, so it's y transpose MA minus J Y, and we get 37 or 372.7, which is the same as up here. The degrees of freedom was the rank associated with that, so it should be 2. Sum of squares for factor B, we should get 31.8, and we do. Degrees of freedom is 6. Sum of squares for air is I minus M, and we get 94.5. Degrees of freedom was 27, the rank of that quadratic matrix in the middle there. Now I'm just going to reprint out the summary so we don't have to keep doing this. And we look at the mean squared error for A, which is the sum of squares for A divided by its degrees of freedom, and it's 186.33. Mean square for factor B is 5.3, 1 if you round. Mean squared error is 3.5. Let's reprint out the summary. And let's calculate the F test. So it's the mean square for factor A divided by MSE, and we get 53, 0.2381. And then for the F value for factor B, or the test for factor B, is 1.5. The P values, we just look at the area in the tail and we get the same as we do up here. Here's this one, and then the next one is 0.211, which is the same as this. Now contrast, I'm going to spend a little more time on it because it's important. So I create two functions basically so I don't have to keep typing the same thing. So the first one is a test to see if that linear combination of the beta parameters is estimable. So you think of it as like the lambda transpose in the part 5 when we're talking about contrast. And so the T stands for test, and then dot estimable, test if it's estimable. And then the G row, it means generate the row parameter. So it's the linear combination of the row space that makes it estimable. So if we create any contrast for factor A and don't bring in the beta the factor B, it's not estimable. And if you look at this, so the test estimable, we should get this back if it's estimable, and we don't. So this linear combination of the betas is not estimable, meaning it's not a unique linear combination. Same thing if we just arbitrarily put a contrast on factor B or the beta parameters, it's not estimable. And let's test it, and we don't get this back. Okay, so here is an estimable function, and I'll explain what it is in a second. First of all, it's tested, and notice we get the same linear combination back. And what this is this one, the first one deals with the mu parameter, and the next 3 are the alpha. So we pick one of those, and then since it's the first one, then we have to pick one of the beta parameters that is nested under that level of factor A. And that's what we do here. And you can do that for any of those combinations. So pick, alpha 2, and then you have to pick one of the beta parameters that are nested with, under that alpha. Now R1 is the row needed to, generate that lambda back. So if we take rho times x, which is this function here, and we should get lambda back. And notice we do. This lambda is equal to this. Now the estimate for this estimable function is rho times m times y, which is 14.25. Or we could just look at the beta parameter for, so that's 1, 2, 3, the third beta parameter, which is this one. If we look at it's the third mean of the betas. If we take the combination. So if we look at beta means, and remember earlier in the program we calculated the means for each of those betas, each for each technician, and we want that third one, and that's what this represents, and it's 14.25. And then, or we could just take a linear combination of that least squares estimate for beta that we calculated earlier, and we get 14.25. And as we should, these are all the same. And the variance associated with that estimable function is 0.875. Now let's look at this estimable function. So here we're taking the second level of A. So that means we have to pick one of these beta parameters that's nested within A. And that's an estimable function. Notice that we get that linear combination back. Now let's generate the row needed for the, it's the linear combination of the row space that we get that alpha back. And that's what we just looked at. We take row 2 times x, we should get L2 back, and we do. Now estimates of this are row 2 my, which is this, or we take the fifth row of the beta matrix, right? So if we look at this linear combination, it's 1, 2, 3, 4 zeros and then a 1. So it's the fifth level of the technicians, and that's what this is saying, 5, 3. 5 is the fifth row, 3 is the third column, which is the means, and it should be 18.75, and it is. Or we can just take a linear combination of the least squares estimates for beta, and we get 18.75. And to me, that is so just mind-boggling, because the least squares estimate for beta, there's an infinite number of them. But yet this specific linear combination of those beta parameters is unique, and it's 18.75. The variance associated with it is that next line. Now, if we're going to do a contrast for the betas, it has to be within a factor level. So the 2, -1, -1 are the betas that are nested under level 1 of factor A. And so we can create a contrast, and it's always estimable. Or we could have done a contrast with the next 3 beta parameters, or the next 3. As long as we stay nested within a level of A, then it's estimable, which means we can develop a unique estimate. And notice we get that back, that linear combination. Here's the row. Row times x, we get our original combination back. And these are the unique estimates, -2.25, or since this is 2, -1, -1, we take 2 times that mean, minus the mean, the second level, and then minus the third level, and we get it back. Or we could just take a linear combination of the beta parameters. Here's the variance associated with it. And this is the last one. And this really is how you take a linear combination or a treatment contrast for the alphas. Okay, so notice that alpha deals with the first 3 parameters, 2, -1, -1. But if you stop there and make all the others 0, then that's not estimable. And so really, to do this contrast, all the betas nested within a level, all their average effect has to be the effect of A. So notice this. So these are the betas that are nested within A. So we take the average, which is 1/3, 1/3, and then times 2, because we took it times 2 here. Now, the factor level 2 of A is a -1. So we take the average of the betas, which is the 1/3, 1/3, 1/3, and then we take it times -1. And then the same way for the next 3 betas. Since this is -1, we average the next 3 betas, the betas under that level, and then take it times -1. And again, so whatever numbers we put here, then we'd have to do the same technique there. And if you notice that it is estimable because we get it back. There's the linear combination of the rows, and so row times x, we get our original linear combination back. And then this is the unique estimate, minus 12.5. And then here we can look at, now notice we're doing the alpha means, right? So we take 2 times this first one, and then minus the second one, minus the third one, and we get minus 12.5 back. Or we could just take the linear combination of the least squares estimate for beta, and we get it back. And here's the variance associated with it if we want to conduct tests. Okay, well, I want to stop here. I have one more video in the hierarchical design, and where we're going to do an R program for nested and crossed designs. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.